Nenomatica, where mathematics meets YouTube excellence. Example: we will solve the equation, the cube root of x plus 2 equals the square root of 2x plus 3. We will proceed step by step, emphasizing the domain, eliminating radicals, simplifying, factoring, and finally checking any potential extraneous solutions. Step 1. Determine the domain. The square root requires its radicand to be non-negative. So 2x plus 3 is greater than or equal to 0, which gives x greater than or equal to negative 3/2. Here is a quick number line picture of the domain, starting at negative 1.5 and extending to the right. Step 2. Eliminate radicals. Because a cube root raised to the 6th power becomes the square of the inside, and a square root raised to the 6th power becomes the cube of the inside, we raise both sides to the 6th power. Step 3. Expand both sides. The left side becomes x squared plus 4x plus 4. The right side becomes 8x cubed plus 36x squared plus 54x plus 27. Step 4. Bring all terms to one side to obtain a cubic equation. Step 5. Factor the cubic. Try x equals negative 1. Substituting gives 0, so x plus 1 is a factor. Divide to get the quadratic 8x squared plus 27x plus 23. Step 6. Solve the factors. From x plus 1 equals 0, we get x equals negative 1. The quadratic 8x squared plus 27x plus 23 has discriminate 27 squared minus 4 times 8 times 23, which is negative, so it has no real solutions. Step 7. Check the domain and the original equation. Our candidate x equals negative 1 satisfies x greater than or equal to negative 3/2. Substituting back, the cube root of 1 equals 1 and the square root of 1 equals 1, so it works and is not extraneous. In this example, we will solve a nested radical equation exactly following a careful domain first, then algebra approach. Here is the problem statement. Step 1. Determine the domain. The inside of each square root must be non-negative, and because a square root equals x, the right side must also be non-negative. From this we obtain our domain condition. Step 2. Square both sides to remove the outer square root. This gives 2 plus the inner square root equals x squared. Step 3. Isolate the inner square root by subtracting 2 from both sides. We obtain square root of x to the 4th plus 2 equals x squared minus 2. Step 4. Enforce that the right side is non-negative because it equals a square root. Thus x squared minus 2 is at least 0, so x squared is at least 2, with x non-negative from our domain. This gives x at least square root of 2. Step 5. X at least square root of 2. Step 5. Square both sides again to remove the remaining square root. We obtain x to the 4th plus 2 equals the square of x squared minus 2. Expanding gives x to the 4th minus 4x squared plus 4. Step 6. Solve the resulting linear equation in x squared. Subtract x to the 4th from both sides and rearrange. We get 4x squared equals 2, so x squared equals 1/2. Step 7. Take square roots to obtain candidates, and then check the domain condition x at least square root of 2. The candidates are plus or minus 1 over square root 2, which equals plus or minus square root 2 over 2. These are approximately plus or minus 0.707, which do not satisfy x at least 1.414. Therefore, both candidates are extraneous. To visualize the domain conflict, here is a quick number line. Square root of 2 marks the. We will solve a radical equation using a precise domain first strategy, then verify by substitution, and finally state the solution set. First, display the word example. Now the problem. Square root of 22x plus 3 plus square root of 2x minus 2 minus square root of 18x plus 7 equals square root of 2 minus 2x. Step 1. Determine the domain, so every radicand is non-negative. The rule is the square root of f of x is defined if and only if f of x is greater than or equal to 0. Apply this to all 4 radicands. Intersecting these inequalities gives x equals 1, the only value meeting all conditions. Step 2. Verify by substitution. Use the substitution rule. If x equals a, Plug everywhere in the equation. Substitute x equals 1. Simplify the inside of each radical. Evaluate the square roots and check equality. Step 3. State the solution set. The solution set contains all values in the domain that satisfy the equation. Therefore, the unique solution is x equals 1. Summary. We enforce the domain of we show the word example, then the problem in bold orange. The equation is square root of 2x plus 2 times square root of 2x minus 1 plus square root of 2x minus 2 times square root of 2x minus 1 equals 2. Step 1. Determine the domain of the equation. We use the rule that a square root is defined only when its radicand is non-negative. From 2x minus 1 greater than or equal to 0, we get x greater than or equal to 1/2. The other two radicands are automatically non-negative when x is at least 1/2. So the domain is x greater than or equal to 1/2. Step 2. Square both sides. We apply the identity open parenthesis, a plus b close parenthesis squared equals a squared plus 2, a b plus b squared. Squaring yields a left side with 3 terms, and the right side equals 4. Step 3. Simplify the squared terms and cancel the opposite radicals. Using that the square of a square root is the radicand, the plus and minus 2 times square root of 2x minus 1 cancel, giving 4x plus twice the square root of the product. Step 4. Apply the difference of squares. Inside the radical we use a squared minus b squared. That becomes 4x plus 2 times the square root of 4x squared minus 4 times open parenthesis 2x minus 1 close parenthesis equals 4. Step 5. Recognize a perfect square inside the radical. 4x squared minus 8x plus 4 is 4 times open parenthesis x minus 1 close parenthesis squared. So we get 4x plus 2 times the square root of 4 times x minus 1 squared equals 4, which simplifies to 4x plus 4 absolute value of x minus 1 equals 4. Step 6. Divide both sides by 4 and simplify. We obtain x plus the absolute value of x minus 1 equals 1. Step 7. Solve the absolute value equation by cases, remembering the domain x at least 1/2. Case 1. X at least 1x plus x minus 1 equals 1, so x equals 1. Case 2, 1/2 less than or equal to x less than 1x minus open parenthesis x minus 1 close parenthesis equals 1, which is an identity, so every x in that interval works. Finally, write the solution set. The solutions are all real x with 1/2 less than or equal to x less than or equal to 1. Now we begin with the first equation. Step 1. Determine the domain. Because we have a square root, the radicand must be non-negative and the denominator forbids x equals 0. Write the domain box. Then record the domain set. Step 2. Compare magnitudes on both sides over the domain. On the left, absolute x plus a square root is at least 1. On the right, 1 over x squared is at most 1 when absolute x is at least 1. Show the comparison rule. Now write the inequalities. Step 3. For both sides to be equal, each must actually equal 1. That forces absolute x equals 1, and 1 over x squared equals 1. State the equality conditions. Therefore, the solutions to the first equation are x equals 1 and x equals -1. Next, we solve the second equation from the image. Step 1 for this equation. Determine the domains. We solve the second equation from the image. Step 1 for this equation. Determine the domain from both radicands. We require x minus 1 at least 0 and 2 minus x at least 0. That confines x to the closed interval from 1 to 2. Step 2. Analyze signs. The left side is a sum of square roots, so it is non-negative. Therefore, the right side, x minus 4, must also be non-negative, which means x at least 4. Step 3. Compare the requirements. The domain says x is between 1 and 2, but the sign requirement says x is at least 4. These sets do not overlap, so there is no real solution. Quick summary. We found x equals plus or minus 1 for the first equation using domain and equality conditions. For the second, the domain and sign requirements contradict, so no solution. X equals plus or minus 1 for the first equation using domain and equality conditions. For the second, the domain and sign requirements contradict, so no solution. For the second, the domain and sign requirements contradict, so no solution. In this example, we will solve the radical equation. First, I will show the problem in bold orange, then we will proceed step by step with domain, inequalities, the equality condition, and finally a verification. Step 1. Determine the domain. For square roots to be defined, each radicand must be non-negative. That means x minus 1 is at least 0 and x is at least 0. Intersecting these gives x greater than or equal to 1. Step 2. Analyze both sides on this domain. When x is at least 1, the left side, square root of x minus 1 plus square root of x, is at least 1. The right side, 1 over x to the fourth, is at most 1. Step 3. Enforce equality. Since the left side is at least 1 and the right side is at most 1 for x at least 1, they can be equal only when both are exactly 1. From 1 over x to the fourth equals 1, we get x to the fourth equals 1. With the domain restriction x greater than or equal to 1, the only solution is x equals 1. Step 4. Verify in the original equation. Substitute x equals 1. The left side becomes square root of 0 plus square root of 1, which is 1. The right side is 1 over 1 to the fourth, which is also 1. Both sides match, therefore x equals 1 is valid. We will show the problem as an example. Step 1. Determine the domain of all square roots. We use the rule that a square root is defined if and only if its radicand is greater than or equal to 0. Now write the 3 inequalities for the 3 radicands. Convert each to interval form and intersect them. We will see that the intersection is empty, so no x satisfies all 3 at once. Step 2. Conclude about solutions. If the domain is empty, the equation has no real solutions. State the conclusion formally and present the final answer. Recap. We followed the algorithm exactly. 1. Write non-negativity for each radicand. 2. Intersect intervals. 3. Because the intersection is empty, there is no real solution. Great work! Example. We will solve the radical equation square root of 5x minus 1 plus square root of x minus 1 equals 2, step by step using the domain first approach. Step 1. Determine the domain of the equation. Both radicands must be non-negative. That means 5x minus 1 is greater than or equal to 0, and x minus 1 is greater than or equal to 0. Taking both together gives x greater than or equal to 1. Step 2. Use the domain to restrict possible solutions. Therefore, any solution must satisfy x greater than or equal to 1. We keep that in mind as we test values. Step 3. Check the boundary point x equals 1. Substitute x equals 1 into the left-hand side. Square root of 5 minus 1 plus square root of 0 equals 2 plus 0, which is 2. That matches the right-hand side. So x equals 1 is a solution. Step 4. Confirm it is the only solution. 4x greater than 1. 5x minus 1 is greater than 4, and x minus 1 is greater than 0. Taking square roots keeps the inequalities because the square root function is increasing. Hence, the left-hand side becomes strictly greater than 2 and cannot equal 2. Therefore, x equals 1 is the unique solution. Before we start, here is a quick challenge. Can you predict the first logical check we must make for this equation? Step 1. Perform careful reading and standardization. We treat the printed symbols as the bold latex you see here, and we note that the square roots require non-negative radicands, which they already satisfy. Step 2. Use basic inequalities for square roots. The square root of any quantity, at least 1, is at least 1. Therefore, each term is at least 1, so the sum is at least 2. Step 3. Handle the equality condition. A sum of two numbers that are each at least 1 equals 2 if, and only if both are exactly 1. So we set the first root equal to 1, and the second root equal to 1, and solve. Step 4. Conclude uniqueness. Since the left side is at least 2 for all x, and equals 2 only when x equals 0, the equation has exactly one solution. A quick visual flurry. In this example, we will solve a radical equation by analyzing domains, and then verifying the candidate solution. Problem statement. Find all real solutions of the equation x squared plus square root of x minus 2 equals 6 minus x. Step 1. Determine the domain imposed by the radical. Since the expression inside the square root must be non-negative, we require x minus 2 greater than or equal to 0. From this we obtain x greater than or equal to 2, so d sub 1 equals the interval from 2 to infinity. Step 2. The left-hand side is x squared plus a non-negative square root. On the domain x at least 2, the smallest value of x squared is 4, occurring at x equals 2, so the entire left side is at least 4. Therefore, the right-hand side must satisfy 6 minus x greater than or equal to 4, which means x less than or equal to 2. We call this domain D sub 2. Step 3. The valid x values must satisfy both conditions. We take the intersection of D sub 1 and D sub 2, which is the singleton set containing 2. Step 4. Verify by substitution. We test x equals 2 in the original equation. On the left we get 2 squared plus the square root of 2 minus 2, which is 4 plus 0. On the right we get 6 minus 2, which is 4. Both sides are equal, so x equals 2 is indeed a solution. Therefore, the solution set is the single value x equals 2. Welcome! In this lesson, we will solve a radical equation by analyzing its domain and the sign of each term. Our equation is square root of x squared minus 1 plus the fourth root of x minus 4 plus the fifth root of x minus 3 equals 0. Step 1. Find where each radical is defined. For the square root of x squared minus 1, we require the radicand to be greater than or equal to 0. That gives x squared minus 1 greater than or equal to 0, which means the absolute value of x is at least 1x less than or equal to negative 1, or x greater than or equal to 1. Let's visualize this on a number line. Step 2. The fourth root of x minus 4 has an even index, so the radicand must be non-negative. That gives x minus 4 greater than or equal to 0, so x is at least 4. On the same number line, shade x greater than or equal to 4 in purple. The intersection of the two domain conditions is simply x greater than or equal to 4. Step 3. The fifth root has an odd index, so it is defined for all real numbers. Moreover, on our domain x at least 4, x minus 3 is at least 1, so the fifth root of x minus 3 is strictly positive. Step 4. Combine signs on the domain x at least 4. Square root of x squared minus 1 is non-negative. Fourth root of x minus 4 is non-negative. Fifth root of x minus 3 is strictly positive. Therefore, the entire left-hand side is strictly positive for every allowed x, so it can never equal 0. There are no real solutions. Quick check at x equals 4. The expression becomes square root of 15 plus 0 plus the fifth root of 1, which is strictly positive. Summary. We found the common domain x at least 4. Noted each radical is non-negative, and the fifth root term is strictly positive, so the sum is always positive and the equation has no real solution. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. Nenomatica, where mathematics meets YouTube excellence.